Okay, so let me see. We do chapter 7, fundamental laws of mechanics. Okay, the fundamental laws of mechanics dealing with mass, momentum, energy, and entropy are stated and briefly discussed in this chapter. These concepts have long histories, and it is not necessary or appropriate in a study of continuum mechanics to elaborate on these topics. The history is not necessary. Our discussion is based on the elementary ideas we have gathered from our earlier studies of statistics, dynamics, and thermodynamics. Okay, 7.1 mass. With each body, we associate a measure called mass, which is non-negative and additive. It is assumed to be invariant under the class of motions encountered in engineering, with a lower limit on the length scales mentioned in Chapter 1. We treat mass as continuous and define the mass density rho as rho is like this. So this V, this is density, the kilogram per unit volume. With this, the mass of a body occupying a volume V can be expressed as small m is integration of density with volume, and integrals. What is this? M. This is very strange. This is very strange. I don't know much. So is F is a mass of a function of mass? Is F is a function of mass? You integrate m dm maybe, and this is you change variable, so you change m to v volume, f inside bracket you have this one, right? V rho dv. Am I correct? Then dm is rho dv. So this is rho dm dv. This is very strange. If it is homogeneous, I think it's I think underlying assumption is rho is constant. If the density is constant with position. Rho is constant with position. Yeah, I think so. Under this assumption, I think this is correct. So what I mean is this is rho dm dV because dm is rho dV. Okay, anyway. The following mass integrals play important roles in mechanics. Total mass. I don't know. Is this total mass? Is it strange? Like here, okay, if you do integration like 1 to 10 dx, this is 10. No? How can mass be a variable? See, this is 1 to 0, 1 to 10. And this is 10. Conceptually strange. I don't understand. Okay, linear momentum. Linear momentum. Very, 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 very strange. Linear momentum. I don't know if is v is a function of m and dm. You and you say you call this linear momentum. It's a little bit strange. Okay, anyway, moment of momentum or angular momentum. Again, does this means okay x as a function of m plus v as a function of m, then dm? This is very strange, I would say, because in the beginning we see each body with each body we associate a measure called mass, which is non-negative and additive. It is assumed to be invariant under the class of motion encountered in engineering. See, I think this is more natural. If the mass or density is proper, I think if the density is a function of position, for example, then if you integrate this one to v, some v, then you obtain mass. This is natural. So this is this way. This is so dv is more like dx, dy, dz. So this is not natural, but then to use m as a variable, I would think it is strange. I think it's strange. You can say, okay, this one, rho can be a function of position. Then dv is like dx, dy, dz. Then you integrate f, then you integrate this one. This makes sense. Then if f is a function of position, I would say, then f can be a function of position. But if m is a function of mass, mass can be expressed like this using integral. But then it's strange. Okay, anyway. So here, in this case, the position is a function of mass. This is strange, I think. Position is a function of mass. Velocity is a function of mass. Then we integrate this cross product as a function of mass for some total mass. Although this relation is based on the assumption that the moment is taken about the origin. The moment is taken about the origin. We are free to select any convenient point. We are select about origin. See, if you have like this, you have origin, then you have x, you have some point. So this has some velocity. Then this point is x, velocity is v. So v, x cross v is like angular momentum. If you multiply m, this is angular momentum. But if you take other origin, you will have something like this. X plus this. Is it strange? Okay, so you can consider x, it's like cosine omega t, sine omega t, v is omega sine, this is more like this, sine sine omega t minus sine omega t cosine omega t. Okay, so then if you consider cross product, think you have one. So x cross v, this is you obtain 001. See, you can consider this way. The last entry is 0. Then you have 001, eh? So but then if you have this extra x, which is constant, yeah, you just have some more complicated angular momentum. But this is like 001 plus large X cross V. So this one is complicated because this X is constant vector. So you can shift origin, but then the angular momentum become complicated. So you have kinetic energy. This is also interesting. V dot V, and you integrate with M. See, the strange thing is we don't have any concept of size. We don't know how big it is. We just have momentum. No. Mass. Then mass V is a function of mass times V is a function of mass. Then we integrate with respect to mass. Okay, anyway. Internal energy. So internal energy, some energy is a function of mass. Then we integrate. This is strange. Internal energy. This is the internal energy density. Because internal energy density, you can say this is a function of position. Is that right? So then the density is also a function of position. Then you have dV. So dV can be dx, dy, dz. dx, dy, dz. Then if you integrate this over some area, region V, then it makes sense. But if you take mass m as a parameter, this sounds strange. At least to me, this sounds strange. Yeah, then you have entropy. Entropy is again a function integrate over m, and small m is entropy density. And this is a function of m. But to me, the more natural thing is if we think entropy density is a function of position. Yeah. We will modify some of these integrals to include microstructural details with additional degrees of freedom, such as micro rotations, on top of the three displacement components. We will modify some of these integrals to include microstructural details with additional degrees of freedom, such as micro rotations, on top of the three displacement components. Is three displacement component? Does this mean dx, dx, dy, dz? See, I don't know why does he use m as a parameter. I think it's more natural to use this one as a parameter. Anyway, so conservation and balance law. Conservation and balance laws. Conservation of mass. The law of conservation of mass states that total mass of a body remains invariant under any motion. I think this makes sense because in this case the density law is a function of position. So this law is also a function of position. Then you have like V0 here. This is the volume V0, and this is the volume V. So you just take integration. You integrate over all volume. So you get a mass m. And after deformation, you still integrate all volume of material, and you get a same value of m. So this is conserved. Balance of linear momentum. The time rate of change of linear momentum is equal to the applied force acting on the body. So this one is okay. This I can accept because rho is a function of position. Then dv is more like dx, dy, dz. You integrate over all positions. That's F. But the funny thing here is, I think this one, I don't know, is this a material coordinate or a spatial coordinate? That's the question. Material coordinate or spatial coordinate? Here is material coordinate or spatial coordinate. I think spatial coordinate, right? This is a spatial coordinate. Anyway, balance of angular momentum. The time rate of change of angular momentum about a fixed point is equal to the applied moment about the same fixed point m. So rate of change in angular momentum is torque. Torque is applied moment. Torque. Here we modify the classical moment of momentum, rho x cross v, by adding a microstructural spin angular momentum, rho j dot mu, with rho j representing inertia and mu the angular velocity. We will discuss the significance of this complication in Chapter 9. The two balance law previously stated without complication in the global form are called Euler equation of motion. We will discuss the significance of this complication in Chapter 9. Two balance laws previously stated without complication in the global form are called Euler equation of motion. Two balance law. This one, balance of linear momentum, balance of angular momentum. So does this mean, okay, we don't add this without complication? So two balance law, this law and this law. These two laws are called two balance laws previously stated in the global form are called Euler equations. Previously stated. Previously or just stated? Just stated. Without a complication. Balance of energy. The time rate of change of the sum of the kinetic and the internal energies is equal to the rate of flow of energies into rate of change of the sum of kinetic and internal energies is equal to the rate of flow of energy into the body of all possible energies flowing into the body, we concentrate mainly on the mechanical power input and the rate of heat energy entering the body, where P is the mechanical power input and H is the rate of flow of heat energy. This statement is also known as first principle of thermodynamics. 7.2.5 Entropy production. In any irreversible process taking place in a closed system, the rate of entropy produced has to be positive. The total entropy change can be written as the sum of the entropy change that is due to reversible process SE and irreversible process SI. Any irreversible process taking place in a closed system, the rate of entropy produced has to be positive. Okay? The total entropy change can be written as the sum of the entropy change that is due to reversible processes SE and irreversible processes SI. The entropy production inequality, or the second law of the thermostatics, states that dSi dt is larger than or equal to 0. Rate of entropy produced has to be positive. In any irreversible process taking place in a closed system, the rate of entropy produced has to be positive. Total entropy change can be written as the sum of entropy change that is due to reversible process and irreversible process. This is sum. Strange, strange sentence. I think it's strange. Okay, this he talk about irreversible process here. He talks about irreversible process here. This is irreversible process. Okay. Then he talk about here. This one. This one. This part is reversible process and irreversible process. So red part, this is only irreversible process. The rate of entropy produced has to be positive. Then this part is reversible and irreversible. This is total entropy. But then again we go back to the irreversible. So this and this is this First sentence and third sentence are stating same thing, with the equality applicable if there is no irreversible process involved. We will discuss this principle in more detail in chapter 9. Okay, we have to wait until chapter 9. Axiom on material frame difference, indifference. Okay, let me stop here. Then I will continue in the next video.